my name is Christine Hauser, and I work on seismic waves that travel through the planet and use that to map out the interior, and we'll get into what that means in a minute. The important thing that you take away tonight is that earthquakes shape our planet. This is a map of the Earth, and you can see the continents are in yellow, so this is the elevation above sea level. And here are the ocean basins plotted in blue. The ocean's been stripped away, and you can see the elevation of the sea floor. And these are earthquakes between 1960 and 1980 are the red dots. And this is when we started to have a global seismic network where we could get good earthquake locations, where we started to have satellites where we could measure the things and see the Earth, see the topography and the elevation of the seafloor. And you can see there's these mountain ranges, and that the earthquakes happen along the peaks of the mountain ranges, and earthquakes continue along the Western Pacific. Here we are in Japan, and we see earthquakes also happening in collision zones between India and Eurasia. So what's very important here is that the movement, the deformation of the planet is concentrated in these very narrow zones. And the question that drove me ever since I was a child was, how can a planet be so active? How can a planet that's made of rock have all of this movement, create all these earthquakes, form mountain ranges in the middle of oceans? How can a planet do this? And I would spend my time with my grandparents each summer, and they had a giant National Geographic Atlas of the world. And I would spend so much time looking at these maps and trying to understand, how can a planet make all of these features? And during my time at ELSI, I've grown to appreciate the connections between earthquakes and life. Planets and the life emerge from the same processes. So the same physics and chemistry at work to make a planet continue on and make it possible for a planet to make life. And life, and here when I say life, I mean life as we would know it. So we're mostly water-based life, and we live on a planet that has an atmosphere, oceans. We walk around on a rocky crust surface. So when I say a rocky planet or planet, I'm talking about a planet that has the features similar to Earth and life that has features similar to us. Earthquakes are a part of this planet-scale dynamic network that provides the environments for life to develop and evolve. And here, evolve is important because it's change over time. And so I'll argue that the planet changes over time, which allows life to develop and change over time. So we're going to start at the beginning. So first you have what we call the Big Bang. We believe this happened around 13.5 billion years ago. And eventually you have the element hydrogen, which is one proton and one electron. And then the hydrogen forms when the hydrogen comes together and it gathers so much gravity, it causes fusion of hydrogen into helium. And this is what happens in the middle of a star. And then at the end of the star's life, it can very large stars can explode into supernova, which creates even higher atomic numbers. So atomic number being how many protons. So it takes many generations of stars to form the elements that our planet is made of, mostly oxygen, magnesium, silicon, and iron. And then sometime later, here 4.5 billion years, is the age of our solar system, where you have these elements in abundance to be able to create planets as we know them. And one important thing here is that iron has a much higher atomic number than oxygen, magnesium, and silicon. And this makes it more dense. So this is an artist's depiction of what the solar system might have looked like after the sun formed. And there's this leftover dust and gas after star formation, and that's what makes planets. It's just leftover dust and gas. And the NAOJ, through its ALMA array, actually makes observations of these protoplanetary disks as they're forming around new stars elsewhere in the galaxy. And one of the things that we've learned over the past couple decades is that there are planets around other stars. And we see the pattern of planets can be very, very different. And so in our solar system, we have the outer planets, the gas giants like Jupiter and Saturn, and we have an inner solar system inside the asteroid belt with planets that are more rocky. And these planets have common features, and I'll explain why that is right now. We have the elements that the Earth is made of: oxygen, iron, magnesium, and silicon are the dominant elements. But as I said, iron is more dense, and in the planetary formation process, you have a lot of collisions, you're creating a lot of heat, you have a lot of radioactive decay. Once you get the iron to a melting temperature, then the iron starts to separate from the more rocky elements, the magnesium, oxygen, and silica. And the iron sinks to the center. And this is true for all of our inner solar system bodies that we've measured so far. So you end up with a liquid iron core, and then you have a mantle made mostly of magnesium, oxygen, and silica, forming the rocky mantle. And if we look inside the layers of our planet, we observe that we have a solid inner core, and we think this inner core is probably around 1 billion years old if we look at the Earth's heat loss over time. And we know about the inner layering of the Earth through seismic waves. And I'll go more into this in a little bit, but these kind of rays show how a seismic wave would travel from here to other parts of the planet. And there's this shadow zone for S waves because S waves or shear waves cannot travel through liquids. So that's how we know we have a liquid outer core. It also powers the dynamo in the liquid outer core powers our magnetic field. And then the mantle is subdivided into separate regions based on the properties of the seismic waves that travel through them. And then at the top, we have the crust. The crust is what happens when you partially melt the mantle rock, and so it's lighter, it rises to the surface. And then we have the liquid, our liquid ocean, and our gas atmosphere at the top. So if we take a step back, we think that we're observers from another planet, which we sort of are, and we look at the other planets in the inner solar system. We have Mercury, Venus, Earth, and Mars. And I've plotted the elevation of the planets. Actually, this is a plot I got from this website, but there are different color scales and different scale heights. But in general, you can see that Mercury is heavily cratered, and this is a signal that it has very little atmosphere. Venus, however, if you look at its surface, looks very different, and most of the features are concentrated near the equator. We don't know a lot about Venus, so we don't have a good explanation for all of these. Mars, we can see volcanoes, we can see deep valleys and craters, and it appears that Mars had a very active water cycle early in its history for about the first 1 billion years, but then that water cycle stopped. And then we have Earth, and Earth looks very different. We have these regions we call continents. These sit at a high elevation. And then we have the ocean floor, which sits below the sea level. We don't typically look at the ocean floor because when we see images of Earth, we look at the oceans. But if you strip away the oceans and you look at the ocean floor, there's a lot of interesting features and islands. And especially in this hemisphere, you can see a lot of structure that's happening in the oceans. But then we can take a step back and think, well, what would it look like when we look at these planets through the visible eye and at their actual relative size? Mercury is very small, and that's part of why it has no atmosphere. It's too small to retain one, and so it's heavily cratered. Venus, however, it seems to have released all of the gases that it formed with into the atmosphere. So Earth stores a lot of gases in rock, and is part of the water and carbon and rock cycles. But it seems that Venus, for some reason, evolved very differently. We have different theories about why that takes place, but you end up with most of the gas in the atmosphere. This puts all the carbon in the atmosphere, which makes the surface very high pressure and very high temperature. So life as we know it can't exist on Venus because it's actually lost all of its hydrogen to space because it's released it into the atmosphere. Mars has also lost all of its hydrogen space because it's so small. So it had water cycle for about the first 1 billion years, and then it seems that It just wasn't able to retain the water because of its size. However, Earth, just looking at it with the visible with your eye, you can see blue oceans, you can see liquid oceans, you can see water vapor clouds, then you can see the land, you can see flat dry land here, and you can see the green vegetated land. So just with the eye, you can tell that Earth is probably the planet that's hosting life. So we say Earth is in the sweet spot. And that is, it's the distance from the sun is the right temperature to cycle water between its phases, solid ice, liquid water, and water gas. And this is really important. A lot of times we talk about whether planets can host life, and we say if they have liquid water at the surface. But I think what's more important is that we have water in all three phases, and that permits us to have these cycles. And the size is right to trap enough hydrogen to develop a water cycle, but not so much that there's no dry land. So if the Earth were bigger and it trapped more hydrogen in the planet formation process, then we may not have any dry land, and then we would cut off that cycle. And the temperature and size are right for rock to be both brittle, so it can break, causing earthquakes, or it can be mobile, it can flow in its interior, which allows it to be mobile and be able to break. And this is how we think Earth is capable of hosting what we call plate tectonics. Now, plate tectonics is unique to Earth because we have these, plates are defined by the presence of earthquakes. So it's these narrow zones where the earthquakes occur that define the edges of what we call the plates. And we call them plates because they're like a plate that you eat on. They're very solid and stiff. All the motion is concentrated at the edges. And here's Japan. There's the Pacific plate, the Philippine plate, Eurasian plate, and North American plate are coming together to make Japan a very unique environment. And so it's this, but the planet self-organized itself this way because it can be stiff in the interiors of plates and it can deform at the edges. And now I'm going to go into how this operates in more detail and how this connects to the interior of the planet. So at these mid-ocean ridges, so these mountains in the middle of oceans I showed you earlier, we have the plate here is an ocean plate, and it's being pulled into the subduction zone here. And so as these plates are being ripped apart, the mantle flow, warm mantle flows up, and then it reaches, some of the minerals reach a melting point, and so you have partial melt that becomes basalt. And you might be familiar with basalt because you often see it building the castle walls in Japan. It's this dark black rock. And so as the plate is carried across the ocean floor, it eventually sinks into the subduction zone. And during this process, the water and the rock come in contact. And when water and basalt come in contact in certain cases, it can make the rock serpentine or this rock serpentinite. So the water gets incorporated in the crystal structure. It actually changes the properties of the rock. And so it turns green. And you might recognize serpentinite because it's often displayed as the signature rocks in Japanese gardens. And but when the plate goes down, when this oceanic plate falls into the mantle, it carries the rock and recycles the nutrients in the rock, the elements and the minerals there. However, the water, this hydrogen that was stored in the crystal structure of the rock, is not compatible at high temperatures and pressures. And the hydrogen's released, and hydrogen lowers the melting temperature, which causes the melting, and those magmas rise and form volcanoes, and that's how Japan is formed. And that's why Japan is so volcanically active, is because the plates are subducting, causing this melt. And so this is how the planet functions and recycles material, rock material deep into the interior, but it also recycles the water and carbon and things back into the atmosphere. And so the planet's able to cycle itself. And I'm going to go into some ways that Japan is special. As I mentioned earlier, we have four plates colliding here. So this is a plot of all the earthquakes that have happened in Japan above a magnitude 4.5 since I arrived in 2013. And you might notice that you can't even see the landform of Japan for all of the earthquakes that are plotted when you plot them in this way. So in this plot, the purples and blues are shallow and the reds are deep. So this is the Pacific plate, and this is the Philippine Sea plate, and here's Eurasia, North America. Now I'm going to look at the earthquakes that are happening. This is looking below the surface. So the earthquakes at the surface outline the edges of plates. But the earthquakes, when the subduction zones actually continue down with the plate to about 700 kilometers. And so the earthquakes actually show us how the planet's recycling itself. And this is one of the key features that makes our planet unique. And Japan is host to not just one, but two subducting plates. And another way Japan is unique, and we have beautiful Fujisan, which could be seen today. So we have Fujisan sits at around 4 kilometers elevation above sea level. But if we look below sea level at the trench, that's 7 kilometers. So if we look at the total change in elevation between the trench and the top of Fujisan, that's around 11 kilometers. And this is very extreme for the planet Earth. And it's not only extreme for the planet Earth, it's extreme for our solar system. So if we look at the height of Everest above sea level, it's around 9 kilometers. And if we look at Venus, we see its maximum height is around 11 kilometers, Mercury around 10 kilometers. Mars, of course, is the king with Olympus Mons at 22 kilometers. But Fujisan, so this area, this Kanto region, is unique on a unique planet because it's so active with all of these plates converging here. And that's why we have such a high risk for earthquakes and landslides and volcanoes. And one of the special things about being at ELSI, as I said, is that it was bringing different groups together. So in 2016, I traveled to Europe and I was at a plate tectonics workshop. And people were sort of agonizing over how are we going to define plate tectonics so that we could, if we were trying to identify plate tectonics on another planet. And then I came back to ELSI, and there was a conference on the philosophy of the history of the philosophy of origins of life. And it's not the type of conference I would normally get to go to as a seismologist, but since it was happening at ELSI, I thought, okay, I should see what they are talking about. And it was like being at the same workshop. They spent the whole time agonizing over how you define life. What is life? And we could see how these two communities were grappling with the same problem because both of these are features that develop on a planet. And so defining them is very difficult because they come from planetary processes that organize themselves. So I'm going to show this animation of earthquakes starting in 2001. And the purpose is not about the details, but to see how earthquakes kind of light up the planet. So when the earthquake happens, the size of the circle is relative to the magnitude. Here, the orange and reds are shallow and the blues and purples are deep. And after an earthquake happens, you see kind of a sparkle. So when viewed in this kind of sped up, where 1 second is 30 days, you can see how earthquakes just really light up the planet and that they show just how dynamic the planet is at these time scales. But we can go to even greater time scales and look at the history of plate tectonics. So there are researchers that look at where the continents and oceans used to be, and this is a recent research result where they took it all the way back 1 billion years and created this movie of plate tectonics. Give it a second, there we go. So the movie's going to play starting 1 billion years ago, so the Earth isn't going to look much like you recognize it yet. The red regions with the triangles are the subduction zones, and the gray lines are places where they estimate mid-ocean ridges to be. Now, the ocean floor is consumed very quickly. So the oldest ocean floor is actually the Pacific offshore Japan, around 180 million years old, whereas some of the continents' rocks go back 3 billion years. So now the Earth is shaping, we're forming Pangea, and now we have splitting the mid-ocean, the mid-Atlantic ridge. So this is sort of what the Earth looks like today. And when viewed at this very long time scales, you can see how active and how dynamic our planet is and how it's changing over time. Now we're going to take a step back and go deep into the planet. And not only does the location of earthquakes and the pattern of earthquakes tell us about how the planet changes, the earthquakes actually illuminate our planet all the way down to the core mantle boundary and even the deepest core. And earthquake waves reveal how these deep forces that maintain plate tectonics and earthquakes at the surface and also sustain life. So this is a movie showing seismic waves. This will be, so the earthquake's going to happen here in just a sec. There we go. So when an earthquake happens, it releases different types of waves. The first wave that arrives at a seismogram, we call the P wave for primary, and you'll see it appear here. The next wave to arrive is the S wave or secondary or shear wave, and here you see arriving at the seismogram. And the slower waves are called the surface waves. And this is important for earthquake early warning because scientists are able to use the difference in the P and S arrivals and estimates of amplitude to try to get a very quick estimate of how big an earthquake is and where it is. And so it's these different types of waves that that's how earthquake early warning works, because the surface waves are the bigger amplitude waves and more damaging. And this movie is a simulation of how earthquakes travel through the planet. And I really like this animation because it's based on calculations of how the Earth moves in these very imperceptible ways to us, but in the ways that seismometers can detect. And after the Great East Japan earthquake in 2011, this is a computer simulation of the seismic waves, these body waves, the P and S waves that were traveling through the planet. And the important thing here is that the earthquake waves light up the planet. They illuminate the interior in a way that we wouldn't be able to see otherwise. So this energy floods the planet, and in places where we have seismometers, we can get some information about what's happening in the interior. So plate tectonics, the driving forces are rooted very deep in our planet. This is an image from my work using S-wave arrival times to determine velocity maps of the Earth's mantle, where blue is fast velocity rock and red is slow velocity rock. Here's the core mantle boundary, almost 3,000 kilometers deep. This is around the top of the lower mantle. Here's the surface, a bunch of earthquakes plotted at the top. We're looking at the Pacific from the side, from the south. And these fast regions, these blue regions, are the subducting plates falling across the mantle all the way down to the core mantle boundary. And then we see these red slow regions at the core mantle boundary, which seem to be associated with hot spots like Hawaii and Iceland. So these seem to represent some type of slow material, some type of warm material that's sitting at the core mantle boundary, but it seems to have stayed there for long periods of time. And so these features show us how the Earth is circulating in 3 dimensions. So we have this concentration of deformation at the edges of plates at the surface. We also have a concentration of deformation along these circulation paths inside the Earth. And this is possible because rock is both brittle and ductile. It can move and it can break. So here we can look at the Earth as an evolving planet. This is a movie that was made to show some history of plate tectonics. So this is the surface, and this is actually a map of density inside the Earth. And so it's going to take us back in time to around the time after the extinction of the dinosaurs. So here we see the opening of the mid-Atlantic ridge, and here's Africa colliding with Eurasia, and these dark blue regions show how these subducting plates are falling down, and this is the core mantle boundary. So this is a movie that demonstrates what I was trying to show with the still image earlier, is that you have this whole planetary circulation, and this is all self-organized just by the physics of the way the rock is able to move with the type of planet and composition we have. So Earth is also in this sweet spot for cycles. We have seasons from the tilt and our orbit around the sun. We have night and day from rotation. We have a water cycle. We have a carbon cycle where carbon can enter rock and then it can enter the atmosphere and the water. We have a nitrogen cycle where nitrogen doesn't get stored in deep rocks, so most of our nitrogen's at the surface, which is most of our atmosphere. And so it's the ability for the planet to cycle not just one thing, but many of these things that provides the feedbacks for planetary circulation. So evolving life is possible on an evolving planet. Earthquakes and life are both self-organizing processes that develop on a planet where air, ice, water, rock, and metal develop the networks and the feedbacks that sustain their existence. And once they get going, then the system sustains itself. So what do earthquakes tell us about life on Earth? They illuminate the fact that evolving life arises on an evolving planet. And with that, I can take questions. Thank you.